Good morning. Am I audible?
Yes, sir.
Okay. So let's wait for 2 minutes and then we'll start. Okay, let us start. Good morning, friends. We'll continue on the software testing and maintenance discussions. So, what we have looked at is in depth in terms of the overall verification and validation strategies. I hope the slide is visible now, right?
Yes, sir, it is visible.
So we have looked at a variety of black box testing strategies. We have looked at a wide range of white box testing strategies also, covering the coverage based testing as well as fault directed testing. Now we will get into the discussion of a number of processes that are critical for development and for maintenance. So we start with the discussion of processes which are more, significant for development, and then we will discuss those which are more significant for maintenance. But I must underline here that all the processes are required both at the development stage as well as is the maintenance stage. It's more to do with the life cycle phase as to where I am, but the processes that I follow must be consistent across the organization. So I highlight here a list of the important, or I should say, the major processes. All processes are important, of course. So I highlight here some of the major processes. Certainly, in terms of development, design, and coding is very, very important. And we have already had lot of discussions about the considerations in that to maintain quality, to maintain productivity, and so on in module 2 as well as in module 4 in terms of UML and all that. So that part we have done. Next, we will take a quick peek in the debugging process as to when we have a bug reported. How should we go about debugging it? Of course, all of us know debugging, all of you know debugging, and certainly oftentimes you debug till now by your sheer smartness. I mean, certainly you all are very intelligent, very sharp, and so far, mostly you are dealing with systems which are small, maybe a couple of hundred lines of code, or at best, low thousand lines of code, and so on. But when the systems get larger, and when we are in an organization which is much bigger than this class, and you have all kinds of people, some may be really smart, some may be, they may take time to react, and so on. Debugging needs to follow certain processes as well, certain, following certain methods to help. The third is how do we actually, this is very, very important and often is a central to the operations of any software company, is how do you track, how do you manage the issues that are happening on a daily basis? How do you track the bugs? How do you manage them integrated with your workflow culture of the organization and so on? So that's called issue or bug tracking. Certainly there are a variety of testing. Black box, white box are generalized strategies, but the question always is as to at what stage and in what way you apply these strategies for testing your system, and how many times you test it, at what times you test it, and so on. So testing processes will talk primarily about that. Next is the release. Once your software is ready in certain level, depends on life cycle again. Then what do you need to do to release that software? How do you number that software? Version control will mean that you have unique numbering for every release that you have made. And it is possible that if you have a very single kind of single point of access software like the Google Chrome, then at any point of time all customers will use the same version because that's on the web. So you do google.com you download Chrome and you get that version, and then Chrome automatically updates. But in several cases the organization, the company may have customers who are dealing with different versions because of their licensing, because of the kind of payments that they have made, and so on and so forth. So bugs may be coming not only on one version but on multiple versions. So how do you control that version? How do you number versions? What are the kind of industry standards for doing these? Are some of the part of processes we need to discuss about. So release and version control I will discuss mostly at the end under software maintenance, because though they are important for development, but they become significantly business focused once the software has been deployed. Till that it is all within the organization. And we will discuss the debugging, bug tracking, and testing as a part of the development processes. Again, they are important for maintenance, but certainly the amount of initial level debugging you are doing and bug tracking you are doing for development is significantly higher, and the testing that you do is significantly higher. So with those words, let me start by discussing debugging. Debugging methods, you all would know a lot more methods to debug, but this is formally what software engineering normally documents. One is a brute force method, which all of us do all the time. You started doing it while you started off with PDS, that you put printf statements. Basically, what is debugging? The debugging is a process of transforming a black box into a gray box, and if possible, a white box, right? See, you can never achieve 100% white box, because White boxing means that you know every internal of the system. Now, while you are debugging, what do you know? You know the code. Is it a complete white box? Just knowing the code is complete white box? You would wonder that it actually is not, because you know the code, but during execution you do not know the dynamics. You do not know at a certain input data what is the control flow that's actually happening. You do not know exactly at a function call which parameters have been passed and which have been defaulted. You do not know what are the events happening at the hardware level, and so on and so forth. So you need to basically, debugging is about going from a complete black box view. For example, if you can take a function and take a complete black box view, that I give this input, I just check, am I getting this output? That's a debugging we do often, right? And based on that, suppose that black box test fails, then we decide to white box the function, right? Go into the function, check into the statements. And while you are doing that, you may be skipping over a set of statements or a loop because you think it should work properly. So what you need to know is what is the status or the state of your system, possibly in terms of the variables in the function, in terms of the globals, in terms of the states of objects. And you want to know what are the states that happen after the loop has executed. So what you are doing, your loop itself is a black box, and you would like to white box it to see how it is changing the state in every iteration, right? So if you look at very clearly, you will see that debugging is basically a smart way of going from black box to white box. So it's always a gray box matter. I mean, we didn't talk about gray box testing, but debugging overall is actually gray box testing, finding out what you have. Now that is where the smartness come in. So what we do is often while debugging in the brute force method, what we see, how do I white box? I need to know the value of a variable at a certain point. I see that, well, I think I have given correct input, but it is not printing a correct output, right? So there are 5 steps, 5 statements. So I see, okay, I think after the statement 3, this value must have been computed, which is checked in statement 4. So after statement 3, I need to know the value. So I have a white boxing requirement, right? So I will put a print statement. So what does the print statement tell me? The print statement actually gives me the internal state during execution at that point. So my, as we say, the observability of the system increases. Yeah. I'm sure you will have exposure to control system design at some stage in your curriculum. And while you study a control system, you will come across 2 very key ideas. One is called the observability of the system, and the other is called the controllability of the system. The observability of the system talks about that if I have a system, then it could be completely black boxed, which means that I cannot observe anything inside of the system. I can only observe the inputs and the outputs. So it has minimal observability. It could be a hardware circuit which is computing the addition of 2 8-bit numbers. It could be a software function which is finding the GCD of 2 numbers. At the end of the day, everything is a system which has input and output and is a black box. Now, observability talks about that how much of the internal states of the system are known to me. Now, in general, we do not, we use systems as black boxes, like users give input and get output. You can make some estimate about the state of the system possibly by looking at the input and output of a system. but only limited ones. You can guess that am I audible? I'm hearing some other sound. Am I?
Yes, sir. You are audible now.
Okay. So I have very limited observability at that. But if I say from that hardware circuit for an adder, if I draw out certain internal lines in the output or as a pseudo output and can put my monitor on those to see what values am I getting at those internal points, then I will increase the observability. I can keep on doing this, but of course there is always a limit. So I say that nothing is completely black box, because even from a black box, from input output, if you have many of them, you can make some estimate about the states of the system. And nothing is completely white box, because it is not possible, feasible to look at every electronic movement, which is the final white box that you'll possibly have, or the quantum movement in your system. And neither you need that. So debugging is a process of smartly deciding what level of white boxing or what kind of gray boxing you need and at what point. Right? So we achieve that in the brute force method by putting printfs. By putting a printf, we increase the observability of the system. Right? We can see more and more values. So from that we can compute, we can get idea about the internal state and see if the internal states are consistent. If they are not, then we debug further till we find the reason. Okay? The other method, or which I'm sure all of you are using very widely, is using a symbolic debugger. Do not get do not get confused as to why is it called symbolic debugger. There's not much reason for calling them symbolic debugger except the historical one. In the historical time, it was not possible to debug while the program executes. So what you used to do is the program executes and used to create a dump, which the debugger used to read, then map to the symbols of your input source program so that you can understand, and then allow you the debugging. So from there they got the name, and that name continues. Of course, every common IDE, whether you are using Eclipse or you are using Visual Studio, Code Block, any IDE that you're using, it has a built-in debugger. And there are certain things you can do. And you can see each of these is basically deciding as to how much you want to white box and where you want to increase the observability. So breakpoints give you, in terms of control, it tells you where you can increase the observability. At this point, I want to check the state. So I'm white boxing at that point. I can have data breakpoints. I can say that I want to break when X becomes 25, right? I do not know. I mean, X is changing maybe at 200 places in the program, but I want to change. I mean, many debuggers allow that. So that's a data breakpoint. So what you're saying that in terms of my state, X possibly has a significance when it takes the value 25. So I need to know where is it becoming 25. So I'm increasing the observability again. I can single step, step in, step over. These are all controls, granularity controls of how much I want to white box, how much I want to observe, and so on. I can have watch points to continuously see the part of the state in terms of some interesting variables. Now, all of this only gives you observability, which means that you can only observe what is happening in terms of the states and their transition in the program as you debug. But you cannot control the state. That is, if you see that, well, at this point, you have done white boxing for half an hour, and you reach a state where you find, well, this state is what is causing the problem. It has reached this state, but if it has reached this state, then also my program should have worked properly, my exception should have taken place, and so on. Or if I say that if at this point I did not have a wrong state, if I had a correct state, then would my program correctly run? Or I'm trying to create exceptions and I'm not being able to create it from input data. So at the exception point, could I change my state and change it to a value so that the exception will trigger, will be raised, right? So you may want to white box not only to observe, but you may want to white box to also to control. So that is called, in terms of control system, it is called the controllability of the system, right? Now it is clearly that if you cannot observe something, you will not be able to decidedly control it, right? Take it with a pinch of salt, because if I'm putting different inputs, I'm actually controlling internal states, though I cannot observe them. But if I want to decidedly control a particular observation, then I need controllability at that point. So in terms of hardware circuit, is I need an auxiliary input which can set a particular AND gate to, say, producing 0 all the time, to simulate a stuck at 0 fault. Or I want to pass a particular value to a function in terms of a particular parameter, right? So controllability often means, in terms of debugging, that we write some extra code which does this kind of injection. The symbolic debuggers at least allow you to do some controllability, have some controllability or deeper white boxing by allowing you to edit, do simple edits while you are debugging. So you just do the edit on the code and you continue. I mean, the whole code does not get recompiled. That's the edit and debug feature, which is a very, very strong feature. And while you study compiler, you will learn as to how systems, even how is it possible even in C++. Of course, you cannot do a very complex stuff there, but you can do simple things like changing the value of a variable and so on. You can just set that and that will be taken, and for that certain spatial data structure is done in the symbol table to be able to allow you to do that. My core point is to bring you to the concept that when you are, these features of debugging basically increases the controllability of the system, right? The rest of it is intelligence. I mean, there is so far no all proven way that if I do step 1 2 3 4 5 6 7 8 17, then I will be able to rightly white box a system from the black box and get to a gray box system, which is what is required for my current case of debugging, right? So there are other techniques which are commonly used. One is backtracking, that you have been, this will this is particularly important when you have actually localized a bug. This is where it has happened, and you just want to keep on backtracing to see where did it come from. It should not have come at this point. So you have white box to a certain point where you have an inconsistent state, and you want to keep backtracing to see where does first time a improper state change happened, because that is the root of your bug. So that's a standard strategy people follow, and well, it is good in terms of a small part of the system, but in an overall big system it might become unmanageably complex. Other is cause elimination method. Is 90% or maybe more bugs happen out of 10% causes. There are few very standard reason of why the bug has happened, right? So once you are analyzing the bug, one very practical engineering strategy would be first eliminate those one by one, because in that process 90% of the time you will hit the correct bug, because it's about like it's about guessing what possibly has gone wrong. You make that hypothesis, conduct test to eliminate, to make the hypothesis fail, and then proceed again, right? There are certain systematic ways of doing that in terms of fault tree analysis, which originally happened in hardware testing and then have been borrowed in software testing. We are not getting, I mean, I'm not getting into deep of that because we do not have that much time, but just good to know. The another technique which kind of is a refinement of backtracking is called program slicing. So if I'm going backwards, then naturally my search space is in, because if I know the state at a certain point, then that point could have been reached from 3 points. So I need to look at all the 3 points. But it is possible that at this current run, actually I have not come from all the 3 points. I came from only 1 point. So this is this leads to the idea of program slicing, that depending on what I want to observe, could I just take out a subset of the program statements wherein the cause must be there. It cannot be anywhere else. Right? So you slice out the program. So obviously you can mentally do that, but it's effective when you have tools for that. There are tools for that. So you can do the slicing at the static time. Like I have shown here, there is a program which reads and does some sum to it, something meaningless actually. But from this program, I can do a static slicing on sum. I say I want to observe sum. Now, if I want to observe sum, then it is, I do not need to look at this Z declaration or initialization of Z or cout high. I can just look at the rest. Right? So that is the static slicing. Static in the sense that no matter what is the value of n, the answer to sum will always lie within this part of the program only, this part of the slice only. But I can do dynamic slicing also. Some tools allow me dynamic slicing, that I say that I want to look at sum when n is 22. Right? So if I look at that, then you can see that if n is greater than 10, then you have this else. So this else part also disappears. So I have a smaller size. So in that way, in my backtrace with slicing, I have much less workload to do. And therefore, I can go deeper, wider in terms of the program debugging. So these are some of the other tools. I'm not sure if Eclipse provides program slicing. I have not explored. But I'm sure some of the free IDs will also have program slicing. You can try that out. Now, naturally, debugging has a lot of, like coding, you have a lot of guidelines for debugging as well. So follow the organizational guideline would be the requirement. So you must have a thorough understanding of the program. And this itself is a challenge in itself. I mean, how do you create a good understanding of the program design? You may not have been the early developer, right? You may have come to the project after 3 years of that product. So how do you get that knowledge? That knowledge transfer itself is a big challenge. We will talk about it on a different lecture. It may require full redesign, and there are certain common tidbits that common mistakes are: you fix an error, you don't fix the error, you fix the symptom. There's always a difference between the error and the symptom. Symptom is what has manifested. That's the observable value. The error may be because of something else, right? So something wider. So if you just fix the symptom, then the error may still there. For example, absolutely, what should I say? Improper, but I see that, well, on this particular input, I should get output as 5, but I'm getting output as 3. So at the output point, I put a if check on the input value. If the input value is what is giving me the bug, then I just forcibly change it to 5. Right? This will fix the error, fix the symptom. It does not fix the error. You would wonder that would anybody do it? Keep assured that people do such things, because when they are under a lot of time pressure and performance pressure and so on, people do such kind of things as well. But more often people do such mistakes because they cannot distinguish between the symptom and the error. So that's a big requirement. A big issue is if you correct an error, then you may introduce a new error. A bug very often introduces other bugs. So you must make sure that when you fix something, it must not break something that was already fixed, that was already there. So that is where the regression testing becomes very, very important, on which again I will have discussions after the bug tracking. So these are some of the common techniques, and standing today, you will always question as how about AI. Now, obviously, it is an emerging and very, very challenging area. If some of you want to subsequently do research in this, you would be welcome. And so there are two perspectives. One is AI in debugging. The question is, can AI help debugging? Assist debugging, assist in generating test cases smartly, assist in doing the actual debug process, deciding, localizing bugs, and so on. And you will see that dating back, this is one of the oldest reference I could locate. In 1998, in MIT, a professor made a proposal for intelligent debugging assistant using AI. But of course, in recent times, there have been a lot of advances of AI being tried out as a part of debugging toolbox. There's a lot to go still. Debugging is still considered a human excellence problem, but well, AI can improve that productivity. The other, which is an equally challenging problem, I do not know, it may be even more challenging, is how do you debug an AI system? Machine learning systems operate in a completely different way. And often, if it works, also we do not know why it works. If it does not work, we do not know why it does not work. So there has been an emergence of what people are now talking about explainable AI. That is, whatever the outcome you have, can you explain that in non-machine learning terms, in terms of the laws and principles that you know? Can you debug a machine learning system? So as you can see, for the last 4 or 5 years, there have been significant effort in terms of building up tools which can debug, which can visualize typical machine learning libraries. So these are hot, research areas in debugging and AI. Well, now let me take you through a typical debugging life cycle. And this life cycle is kind of common sense, but well, it depends on what the way your organization work, the software development process that it follows. Broadly, these are the life cycle steps that you'll have to do, but in what frequency you do them, in what granularity you do them, in what depth you do them, depends on the organizational policy or the workflows that you follow. So kind of I'm taking a view that, well, your life as a software developer is nothing but a person who fixes issues. Right? You'll do not feel small with this statement, but that's all engineers are for. I mean, there is a problem, and I'm there to solve that. Whatever that solution means, whatever it takes. And once I have solved that, then I move on to the next problem. Solve that. So that's the life of an engineer. So that's the life of a software developer as well, irrespective of what is her role, whether she is a tester, she is a architect, she is a program manager, she is a sheer talented developer, whatever. Right? So if you look at from that perspective, you see the whole cycle starts when you get a issue. I mean, bug and issue are taken to be similar. bug has a sense of negativeness in the way that bug means that something is not working as it should. Issue is little bit more general. It means a bug, it's an issue, but it could also mean that I desire to have a new feature. Right. If I desire to have a new feature which was not there in the specification, I cannot call it a bug of the system, but it's an issue. So, but people use it, particularly in software industry, people use these two terms very interchangeably. So a customer or the QA team, quality assurance team of the company reports a bug on the issue tracker. So there has to be, hundreds of people are raising thousands of issues being fixed by hundreds of people, being reviewed by hundreds of people. Naturally, it cannot happen in a pen and paper method. Right? There needs to be a system which manages all that. I'll talk about that system as well shortly. But let's say there is such a system. So that is where you first report a bug. So that's called the reporting stage of the life cycle. Then once a bug is reported, naturally, let's say it comes to you, then the first thing you have to do is to reproduce the bug. So the bug is saying that this is observable, right? This input and this output is observable. Now you put that on your version of the software, what you have at hand, and see, are you observing that output? Maybe that you don't see that bug. You see correct operation. That's always possible, right? Because the customer is using a different platform. The customer, I mean, you may be using a little endian system and the customer is using a big endian system, right? And some low-level data representation gets marked up on customer system, which is fine in your system. So reproducibility is the first step in the debug life cycle. So in fact, it is also possible that the customer may not have given you the test case. It's just told you the symptom. Many a times, customers have proprietary on the data, that they are contract bound not to release the data outside of their organization. So they find an issue with an input set which they cannot share with you. They just say that this is what is happening. Maybe give a very broad description of the input set, but that's all about it, right? So reproduction is the first challenge. If you cannot do that, you have to go back to the creator and negotiate that. Once it has been reproduced, then you need to localize. Then you need to find out using all those debugging techniques. That is, you are managing how to increase the white boxing of your system to slowly go from, you'll possibly, if it's a complex system, you would like to locate it to the possible submodule, then possible module, then submodule, then possibly have to come to a set of functions and the specific function or a set of functions and then the particular line and all lines and so on, or certain events and so on. So that's called localization. So once you have localized, you have identified that, well, the bug exists and this is why it's happening. Then you have to really do the analysis again. Analysis as to why did it happen. So that analysis is often called RCA, root cause analysis. You can loosely call it as a causal analysis. The causal analysis would say that, well, I'm seeing this bug, so what is the cause for that? It could be because of implementation error. Some code has been wrongly written, like it was to be if x equal to 0, instead x equal to 0 has been written. So every time the condition is checked, actually x is being assigned 0. Right? It's a coding error. It could be a logical error, it could be an algorithmic error, it could be a resource error, concurrency error. So there could be several types of implementation error. It could be at a higher level, it could be a design error, that a functionality was wrongly understood, incompletely specified. It could be a test plan error, that what was missed out in the test plan. Because if the customer found this, the question certainly is you should have found it. So it could be a test plan error, that the wrong things were tested. It could be a documentation error also. For example, several systems, like say, think about C++ standard library. You have so many containers and you have methods on them and so on. So the methods, you try to use a method and you get an error, right? Now, the question is the error because of there is a bug in the method? or in the implementation of the container, or there is an error in your using it. Now, how do you use it? Based on the documentation. So the error could be on the documentation, that there is a special case which the documentation did not talk about. So there could be several possible sources of errors. So you analyze those. That's a causal analysis, and then try to go into the real root of this. The question is it a repeat bug? Did it come before and was fixed and was released, and it is coming again? So the same mistake, I mean, it's the principle of life. The same mistake you are committing again. So you did not learn. So you did not fix. So a repeat bug is always a major kind of, I should say, kind of not a positive thing for whoever handled that bug. Right? So there was something incomplete in that last fix. Either the design was not proper in the fix, or test plan was not proper in the fix, and so on. So you get to that root, so that you can answer why the bug was not caught in your in-house QA. Your in-house QA should have caught that bug. How to guarantee similar issues will not repeat. So this is the in-depth part of the life cycle where you are really analyzing the cause of the bug and your potential as a software developer. I mean, you will be really, really liked by your lead and the manager if you do a RCA, good RCA, because that solves several hours, future hours of what you could have spent, right, without this RCA. Because the more of the RCA you do, what you are ensuring is you are getting to the real root of the error and not fixing the symptom, right? Once that RCA has been done, it is understood what the problem is. So you have to determine a fix for that bug. It will need a maybe small to medium to large design document to be done, test plan to be done for this particular bug, and so on. Then you apply the fix, actually do the coding and all that, and do the testing, do the development test at your end. That must be clean, and then pass on to the QA. They must do the regression test, and it must be clean. The code should be reviewed by your seniors, so that all of these, that the RCA is agreed, the fixed plan, the design is accepted, and the code change is accepted as well. Review can bring that out. We'll talk more about code reviews at a later point, but fix and test is the next thing you do in the life cycle. And then finally, so now it is ready with the fix. So you update the issue tracker, bug tracker, you tag the code for version. I will talk about what does that literally mean. It's basically you have to remember, now you have created a new version of the software. Because in the earlier version that bug exists, in this version the bug does not exist, right? So you have to tag it properly and so on. And then finally make the release, which possibly will be done by the release team or the QA and so on. So this is a typical debugging life cycle that an engineer will go through, even during a complete, I should say, pure development phase where the customer is not there, QA is not there. Often the tasks are divided in this way. So you, in the issue tracker, you do not have a bug, you have a task rather, that the task is implement the login functionality of the system, right? And you go through this entire thing. Maybe you may have a little less RCA to do, but you'll still have to see according to specification what are your targets and so on and so forth. So it is something of an approach, the debugging life cycle, and given that as of the present standard statistics, 30% time the developers are spending on actually writing new code, and 70% of the time the developers are spending in maintaining code, debugging life cycle is the developer's life cycle. Right? So it must be understood, practiced, and the more apt you become in this, the more loved you'll be in the organization. So that's a basic point that I'm trying to make. So there are naturally tools. I was talking about that you need tools for tracking this. So they are called issue tracking. So there are a whole lot of names. Some people call it issue, some call it bug, some call it ticket, some call it change request, whatever. So there are tracking systems which manage them. I have mentioned about two here. One is Bugzilla, which is has been around for ages, and it's open and free software. So you can just start using it. Another is a very advanced one, which is commercial. I have had the benefit of working with this for about 5 years. So it is really, really beautiful, but it's extremely priced, comes from Atlassian. And this software is not only for issue tracking, but it actually integrates with the SDLC stages. So for example, you do not have you may not have a bug report, but you may have a Scrum backlog. Scrum, we define that every day you have a backlog. As to backlog is what is pending to be done in this cycle. So the Scrum backlog is your issue report, and what you are doing is to remove that backlog, right? So that's kind of Scrum backlog is an SDLC entity, and what you have at hand is an issue tracker, Jira. It is integrated. So I have fixed these three issues. By that fixing of these three issues, I have knocked off one backlog item, right? So these kind of tracking can be done. So there are some details I've tried to give. So it's basically what I'm trying to hint at is issue tracking is kind of a life cycle phenomena, which is closely tagged with the workflow of the organization, right? Now, this is looking at that workflow from the perspective of the earlier life cycle was for the debugging, for more
Sir, you are not audible.
Am I audible again? I lost the connection.
Yes, sir.
Okay, I'll go back. So I hope the slide is visible.
Yes, sir.
So here, what I'm trying to show is you can think about, you can personify a bug, a defect, and think about that in the bug tracking system, it passes through different states, which is called the life cycle of the bug, life cycle of the defect. So this is when it arrives. So it's new. Now by itself, nothing will happen to it unless you assign it to a developer. So you assign it to a developer and put it to assigned state. And in the debugging life cycle, this is when the developer gets to know about the bug. So that is kind of in the reporting stage of the debugging life cycle, and the bug is in assigned state. Then the developer works on it, does a lot of things, tries to reproduce, tries to localize, do the RCA, make the fixed plan, fix and test. All of these are going on. So the debugging life cycle is progressing through these stages. But in terms of the bug, it remains active. It has not been resolved as yet. You can obviously create a different state machine. That's what depends on what organizations want to do to show that, well, how far it has progressed. You can show that reproduction, localization, and RCA, you can show by a different state here as, say, analyzed. You can say This is open, active is open, and then if you have reproduced, localized, and done the RCA, then you have analyzed, and then you will fix. You can do that. When I used to run the company, I used to have 2 states for this. Makes it easier to find out where in the debugging life cycle where my developer is. Then it goes to test because it has been fixed. So the defect is fixed, is ready for testing. So then the QA will come and verify, do the fix and test and release. And once it is released, then it becomes closed. It has been done with. Or alternate could be that this verification is failed. So then it goes to reopened and naturally gets back to the same developer as active. This cycle may go on. Alternately, on reproduction or localization or RCA in the active state, the developer may find that there are several reasons that this bug could be rejected. For example, it could be a duplicate bug, something that already exists in the system. Or it may not be a bug, it is actually a feature of the system. Or after all attempts, it could not be reproduced. Since it could not be reproduced, it cannot be fixed. So in those cases, it will be rejected. Or it could be that, well, on RCA, you find that it is, it's going to take 2 months to fix this. And your manager tells you that, well, you don't have to fix it now. We'll schedule it at a later date. So it's deferred. So this is just a representative one. If you look at the net, you'll find every site will give you a different state chart for this because it depends on the priorities or the work processes, workflow of an organization. But there is one which closely handshakes with the debugging lifecycle, and understanding both of these is in the core of how development, debugging, testing happens in the system. Rest of this part is just a few screenshots from Bugzilla. So this is typically the information that you start with: the product, the component, which version, who is reporting, how severe the bug is. Is it a showstopper, like it's crashing the system? Or it's like, well, the message is not nice. And so kind of. What is the hardware and operating system details? A summary line to easily understand, a detailed description. You may have attachments of test cases, and finally you submit the bug. So this is typically the typical information that the cycle in a bug tracking system starts. There could be more information given here in terms of deadline, estimated time, so on and so forth. And at any point of time in the system, one may be able to see the list of bugs that exist. So here you have the ID, the product, there's a component in the product, the assignee who is doing this, there's a summary report, this is a status. Status is a state that I was talking of. So this is from a system where they use a confirmed status for something being inactive. Input status is a new, right? So that's the kind of. Okay, I think let me stop here. I've talked about debugging, starting from the principles down to some of the practices that you should expect and be ready for. So if there are questions, then I'll take it. Any questions on the debugging? I know this sounds little kind of uninteresting grab to you, but this is going to be your life cycle if you decide to remain in the software development field. If you become a consulting manager, it'll be similar, but in a different way. But if you remain in software field, this is going to be your life cycle. So it's important to understand, but at the same time, I do follow that. Well, at your level, it may be looking a little bit boring and abstract, but do keep these presentations with you. Maybe, when you are in the company, maybe it will help you refer to these, because these are, and quite a few of these you will not get in the book, because I didn't take it from the book. So I just assimilated it from my 11 years of running the company. So this is absolutely hands-on what works, not any big theory in software engineering that I'm presenting here.
So for C++, could you recommend some coverage tools that we can use for test coverage?
Use LCOV.
Is that open? Is that free for use?
This GNU. See, first thing is, whenever you want to do something with C, go to GNU project. GNU has made most of the tools, like you have gprof for profiling. You have debuggers,
Yes.
GNU debuggers. You have
GDB.
You have GCOV, LCOV for coverage, right? So GNU has provided for all languages. I should not say all languages, for a large number of languages. But for C, they are a prime source. Like Java has some more free stuff as well. But LCOV,
IntelliGence comes on built in.
I mean, more and more intelligence will come built in. But you remember I did a quick demo of EBM 9K project
yes,
coverage
last
report.
lecture.
So that was in LCOV. So we used to actually in the company we used to use LCOV, and it proved pretty well. The code was not very big. It was 180,000 lines. So 180,000 lines. It used to run on 30 servers, each having 32 cores. So couple of 10,000 thread at the same time, and used to run for a month to simulate a mask. So the coverages used to be computed by that tool. So it was pretty good. You can try that out. I mean, we haven't put all those as a requirement of the assignment, because I know doing so many things in this time is difficult. But if you should do it, you will have a good it's good fun, and you will have a real exposure to what in the company you are expected to do. And if you understand this, then certainly the companies will love you. That's so for software engineering, learning tools is a very, very important thing.
Yeah, tools are the integral part of the business.
Absolutely. As much of it as you can learn. And open and free tools give you about 75 to 80% of what commercial tools give you. Maybe if the company, you join a big company, you will have all commercial tools. But
yeah, they probably have in-house tools as well.
If they are that big, yes.
Yeah.
Of course. No, I'm not actually, because even startups have a lot of in-house tools because they can't afford this.
They can't afford commercial tools.
Like in our company, we had a whole lot of, we had a complete separate toolkit for regression, which we had developed. We spent about 3 man-years to develop that, because whatever was commercially available was not, befitting our business returns. But that worked pretty well. And in fact, at a later point of time, we licensed it to 5 other companies and earned money back. So it works in an interesting manner. Okay, chalo. Let us close now. We will. Tomorrow is a holiday. Tomorrow we will have class. Tomorrow we'll have class. Friday is a holiday. So we'll meet in the second half. 2:15 will be the test for 1 hour on Moodle. The mail may have gone by now, or it will be going right now. All the best for the test. Thank you very much. See you tomorrow in the class.